So imagine an orchestra tuning up before a big concert. Every instrument is playing a different note. You've heard it: strings, horns, percussion, all at once, almost like an elementary school band getting ready to go. It's chaos. Now, that's where a lot of IT environments sound today: the wired, the wireless, the cloud, the hybrid, the edge, all generating constant noise. But when the conductor steps in, that noise becomes music. In our world, combining quality of service and application performance monitoring is that conductor. It brings harmony so you can identify and resolve performance issues before they become full-blown outages. And today, we're going to show you exactly how to turn that IT noise into a well-orchestrated symphony of uptime and user experience. So welcome to Smarter Performance Monitoring for Complex Application Environments. I am thrilled to turn it over to Plixer data scientist Adam. I've been butchering your last name over the last couple of webinars. I believe you've said it before as Howarth. Is that correct?
Correct.
All right. Yeah. Over to you, Adam.
Awesome. Thank you very much, Peter. Yeah, so today we're going to focus on the metrics that can be collected from the network that help support application health, real-time protocol, user experience, and things of that nature. So we'll take a look at some interesting application topologies, ultimately how we can get the metrics we need to make those determinations out of it, and then ultimately how that follows through to differentiated service classifications, getting some control over shaping traffic in order to preserve application or user experience. So just to begin, I want to talk about some of the metrics we'll talk about today. So on the TCP side, so any application that's stateful, we'll be looking at latency metrics, how those are broken down, how we can get an idea of how the latency is impacting the client's network experience, the server's network experience, and then ultimately the application delay itself. I know just from working through lots of kind of knock issues with folks that more often than not, you end up in this little war between maybe an app team, a database team, and the network team trying to troubleshoot, why an application's performance is degraded. And ultimately, a lot of finger pointing starts to happen between, the app team and the network team. So this is going to be a nice set of metrics that we can use to prove, like through hard evidence, that it's not a network problem, it's an application problem, or in the unfortunate case, vice versa, when the network's actually kind of failing the application. Additionally, another metric we'll talk about is jitter for RTP streams. So jitter is always this word that you'll see come up a lot when we're talking about RTP. It is specifically the average inter-arrival time between packets. So I did my best to try and kind of demonstrate that in this graphic just to start to give this weird metric a little bit of intuition. But ultimately, we're looking over the course of a flow, how much variance can be found in the actual delta between the arrival of real-time packets. So when you think of RTP, you're going to think about like the audio that you're hearing over Zoom from me now, the video that we're broadcasting out. And ultimately, anytime you start to hear my voice go robotic, you start to hear that interpolation in between because the application basically has found a gap in the traffic and it needs to put something out. So you start to hear those very long kind of almost auto-tune like notes, where you've had a jitter buffer overrun and the application needs to interpolate what data should be there, all the way down to video, where typically video, you start waving your hands around. Due to compression algorithms and just to be efficient, video will typically just broadcast the actual pixel deltas. So up in these corners where nothing's changing in my view, you're going to have just no update to those pixels versus all the parts that have some motion to them will be the actual content of the RTP payload. So when there's any instability in the inter-arrival time of those packets, again, you can get choppy video, you can get weird kind of jumps in the quality of the media, specifically because the application now has to fill gaps where it didn't have data. Again, this is something you'll see specifically with real-time applications because there's really no way to buffer the state and then play it back smoothly to the user because it's kind of happening in real time. And once we've missed a frame of video, there's really no benefit in the application going back in time and finding that frame and inserting it because it's already kind of streamed past the real-time view portal and it's gone. So those are really the two metrics we'll talk about are latency on the TCP side and jitter on the RTP side. And later on, we'll get a little bit deeper into how those are calculated. But first, I just wanted to start with some example topologies. So if we think about retail, it's a pretty complicated, stack of communication that needs to occur. Previous life, I ran a medium to large size retail network, and this is something that we saw all the time, where your POS system has a few jobs, right? It both needs to facilitate the transaction and get the customer through the line, but it also needs to update inventory about what was sold. It needs to go out and maybe run a credit card payment, look up a customer account, all sorts of things, kind of multi, application endpoints that may need to be reached out. And again, the speed of those interactions is really going to be tied directly to your ability to conduct business. In the case of a POS system, that's where the transactions happen. And ultimately, if the computer is very slow, suddenly lines will back up and you risk kind of the attrition rate of people jumping out of line because I don't have time for those type of situations. So it's a very real example of where application performance can impact business. But you can imagine, this is a POS system. The same things will hold up across really most verticals. If you think in healthcare, somebody meeting with a patient and it's taking forever to get their patient record to show up, that's similarly going to impact that experience. Medical billing, there's a certain amount of times they can spend with patients. They don't want to be spending it all waiting for the computer to pull up data for them. So lots of examples we can think of, but really cases where the actual latency of an application is going to directly impact business performance. So again, in a retail example, we'll have our little local network, our actual POS systems, maybe a store-specific inventory database so they can go back and forth, check, do I actually have this item to sell? Perfect, I do. Subtract one from the whole, the standing inventory, things like that. These are going to be places that are basically at the local access layer for the store. And again, like really the first step in our journey to where we can jump into the network, collect information, and really enumerate how the application's performing. So for just some general background, we are talking about NetFlow and IPFIX here. Typically, when you're talking about NetFlow and IPFIX, you have your key fields. What are the items in a flow that define that flow? You think of the 5-tuple most often: source IP, source port, destination IP, destination port, and protocol. Anytime you have that unique combination go through the device, it'll open an entry in the flow cache and start to collect information about it. The typical collection fields we think of are like packet delta counts, byte delta counts. Those are going to be the things that you use to really enumerate the just general usage of that conversation on the network. But today, what we're exploring are devices like our Flow Pro or Cisco devices that run AVC or many other probes that can actually calculate performance statistics while that entry is open in the flow cache. It exports those in IPFIX and NetFlow data, as we'd expect with everything else, and then ultimately collecting those metrics over a long period of time allow us to not only analyze how an application's performing instantaneously, but rewind time back to the point of an incident. Maybe we're triaging a ticket where a user felt some sort of performance degradation, reported it. It's not happening right now as the investigation begins in the knock, but by collecting these metrics over time, we can actually kind of rewind back to when it all occurred and take a look at the state of things when the actual incident was reported. So again, this is starting at the local access level within like a retail environment as example. These are going to be the first places that we could tap into the network, get an idea of how that POS system is actually communicating with its local infrastructure, and start to break down, is the network a delay? Is the application a delay? You'd imagine at an access layer, there's really not a lot of network to get in the way. So again, it helps us develop evidence to show that applications are slow to respond. As we kind of roll this topology out, there'll be enterprise level authorities. So anything that the local store database can't resolve for a POS system, maybe customer accounts, somebody wants to charge something to an account or use credit they have on an account or loyalty points or whatever type of schema is in place. It's going to be something that isn't the authority for that data isn't in the local store. Maybe you have 1,000 stores. It has to go up to a higher level in the network, maybe haul back to the headquarters, go out to a cloud application, check that information, and again, exposes us to another hop in the network where it may be beneficial to actually get some measurements out of how that's performing. Again, so we can tell, is there a WAN side issue here between the stores and the back end resources? Is it the application? Is it the network? Again, just another observation point that'll be interesting. And then finally, we have kind of the last hop, the cloud services backend. So if that means, there's live sales, live pricing, maybe it's a dynamic. We have a retail chain up here in Maine that is an old kind of record store situation where they will buy and sell things from people who come in. they have the ability on the back end of their system to actually reach out, query the internet, get a fair price for purchasing, used products back from people, and then in real time giving an offer that makes sense for their model. So in that case, right from the POS, you need to actually be able to get all the way out to cloud services that can give you that data. And again, exposing many more hops, maybe a hop between the store and the headquarters, and then headquarters in the cloud, or however they have that traffic shaped. But again, more hops in the network where it's going to be really important to get some latency metrics when we're trying to triage performance incidents later on. So if we think about just kind of an example flow, we'd have our first hop at the local level. We want to get an idea between client, server latency, the actual application latency. Same kind of situation when you actually go to look up that customer account. Now we're going beyond our local access layer. We need to move up into the network a bit. Are there further points that may be causing network side latency? Is there a new application that may be slow? Again, if you think of the POS reaching out to lots of little like microservices to resolve things between inventory, customer information, etc., the application delay may not be consistent across those. And this is another way that we can, by dropping these probes in, have some idea as to, the customer information service actually returns very quickly, but the inventory updates are what's slow. The network doesn't appear to be an issue here, but now we have an idea about what microservices are actually holding up the course of business. And then finally, any jump that's going to have to go out to another external resource, again, exposes another part of the network to us where there may be some sort of slowdown. And again, external applications that we may not even have a local team that's an authority to, but we use basically as a user. Is there delay in those services? Is there something we can escalate up to those cloud offerings that we're using to show, I can prove to you through the metrics I've collected in NetFlow and IPFIX that our client and server delays are actually quite responsive against this application, but anytime a query is made to it, we're being slowed down significantly. And here's actually some hard data that shows that's the case. So it immediately eliminates some of the back and forth that you'd run into in any of those triage scenarios. And then finally, for any kind of PCI vertical, if you have a separate segment, that's going to be really, really sensitive to performance. If you're a large retail environment, you're probably running thousands of credit card transactions a minute. And any slowdown in that or any queuing that ends up happening in that chain will really start to cause a very tangible performance impact that will, again, risk kind of the churn of people who are maybe waiting to check out that are low on time and they're trying to just move through. So again, lots of little connections that add up to a fairly large picture when viewed in the composite. And again, getting insight into all of these individual hops and where the latency can be attributed is going to be super helpful for breaking down any sort of impact that's around these kind of complex multi-hop, multi-service, multi-topology crossing application situations. So again, this is kind of the traditional retail stack where you have lots of layers to it. You're going through the enterprise and then again out to external resources when they're needed. And then more often than not, more on the SMB side of things, you may have entirely cloud-based retail services. So again, any type of issue in these environments, it's going to be more important than ever that you have hard evidence that you've collected and you can actually show that the application is where the delay lies and not any sort of kind of local network issue or queuing issue. So we'll take a look at how these metrics are broken down next. We'll kind of jump into the product and see what they look like, and then we can kind of talk about what that means for setting DSCP values and how things can be retuned in order to fix any sort of network side problem, and then ultimately how we can provide evidence around explicit application problems and kick those over to the teams that can hopefully re-index some table in the database or find ultimately what the slowdown is there. So on the latency side of things, this is actually a pretty clever method that's used for calculating this that breaks us down again into those three tranches of client delay, server delay, and application delay. We'll see those get calculated in an interesting order. But really, this starts with some sort of device that's measuring this traffic. Again, for the Plixer platform, this is a Flow Pro, but we can collect the data just as easily from any device that's able to run these metrics and export it over IPFIX. But the conversation really begins when a client sends the initial SYN packet to a server. The SYN packet goes to initiate the TCP handshake. It passes through our observation point, and at that point in time, a timer starts that is associated to the flow cache for this specific conversation. When the SYN-ACK comes back from the server, we finally have kind of our second piece of information passing through our observation domain, again, the probe or Cisco AVC device, whatever it may be. And now we actually have a measure for the delay moving between our observation point and the server. We saw the SYN go through, started a timer, a SYNAC bounce back off the server, and we can actually now set in stone that that is how long from our observation point it takes network traffic, at least of this class, to move to the server and then back to the observation point. So we have our first measurement at that point, our server network delay. Ultimately, the client will act back, acknowledging that the synchronization acknowledgement came back from the server, and we have a second bounce now that can be used to enumerate our client network delay. So we now, in the first step, SYNAC, we get our server side network delay, ACK to, or SYNAC through, and then the ACK from the client, and we have our client network delay. So at this point, for any of those instances when we were looking at kind of the retail topology, we immediately have an idea from the point we're observing what is the network latency on the client side, what is the network latency on the server side. Two metrics that we can use to either pinpoint kind of what side of an interface our slowdown is occurring or drops or whatever it may be. And then ultimately giving us a place to start framing where in the network a slowdown or performance issue might lie. Finally, after that handshake's completed, the application will send an initial app data request or whatever it's actually going to use that TCP conversation for, and then we'll get a data response from the server itself. And ultimately, what that enables us to do is we now have a composite in that measure. We know what the server-side network delay is from our previous calculation in the handshake. And now there'll be some additional latency that's observed there, and that can be attributed to the application itself. Again, we know what the network delay should be between our observation point and the server. So really anything over that is going to be time that was spent in the application before it could package up the response, throw it on the socket, and fire it back over to us. So in composite, we have our three metrics here. It first calculated our server network delay, then the client network delay, and then ultimately the composite of the server network delay and application delay. So the final part of the process for the calculation that's happening against the flow cache, it will subtract out that network delay from the application delay or the overall delta that was observed during the app request and app response, and leave us with just a pure application delay. So we now have those three metrics. And again, this is very powerful, specifically when kind of going back and forth with an application team, where it's not speculative, it seems as if we can actually show in hard data, this is the delay between our observation point and the client, this is our delay between the observation point and the server, and this is ultimately how much time was spent waiting on the application to respond. And again, subtracting that server network delay out is really the powerful part, because that's what completely removes all of our network state from the actual time spent dwelling in the application. So again, if the application's high, we can point to the app team. If server or client network delay is high, then we already know it's something that we can solve from the NOC perspective. Secondly, thinking about RTP and jitter, RTP is stateless. It's effectively the client or the server spraying data at a listener. And ultimately in RTP conversations, those applications are working around a jitter buffer. So a jitter buffer is meant to absorb some variance in the inter-arrival time of packets. It's typically like 30 milliseconds. So if you think about humans, we are interfacing with the world with a delay of like 100 plus milliseconds, between 100 and 200 milliseconds. So ultimately, anything down at like 30 milliseconds is going to be far below our ability to perceive a difference. So when a packet, has some variability between how much time has passed since the previous RTP packet arrived and the next one's coming, we have that 30 millisecond jitter buffer in the application to absorb those things. What's really important is understanding with our applications how sensitive that buffer is going to be, and then ultimately getting these measures off the network to figure out how much variance is in that time delay or time delta between packets, and comparing it against the jitter buffer to see, is this inter-arrival variance high enough to result in a observable performance impact in the application, getting to the point where voice starts to break down or video starts to get kind of choppy and weird. So you can start to see if there's one kind of bend in one of these lines, we get a much bigger delta between packets. You may run into a case where the time between packets is longer than that jitter buffer, and that's when the actual performance impact will start to be felt by whoever's using that real-time application. Whether it's security cameras that are just recording everything. Typically, security cameras are at much lower frame rate. You don't really want to drop a packet because that's, the lower the frame rate, the bigger the deltas that were happening per frame. If you lose any of that data, it fails to make the jitter buffer in time in order to be recorded. You end up with basically half the frame rate for that period of time and lots of information loss in between. Similarly, with voice calls, you start to drop or start to get large delays in the voice data that's coming. It doesn't necessarily have to be dropped altogether, but if it gets there too late for the application to use it, then real time's already passed and it's really not helping anyone to play some vowel sounds that I made a second and a half ago now, since the context of real time and real time protocol is actually what's important. So I just quickly want to pivot over to the actual product itself and take a look at what working with this data looks like. So from a very high level on the Plixer platform, really the goal, we have lots of ways of interfacing with data, getting views from different devices, looking at different contexts of the traffic, however we're trying to solve problems. Orchestrating these things into dashboard views is really kind of the end goal of the platform, finding the data that's important to you, finding the information that helps you solve issues the most regularly, and exposing that in a place where you have quick access to it. You don't need to do kind of a whole research study in order to drill in and find what you're looking for every time, you work through a similar path. So in this view, we have lots of kind of generic information, our top interface use at a site, various policies that have been violated from a lot of the security and performance algorithms that run on the platform, things about the top hosts, the top applications, top users, if you have devices that can actually attribute the user, or you're using our AD integration to attribute IP and user timeframes together. But then ultimately we have a view here for application latencies. So we can now look at a site and specifically look for places where just the application latency is high. Similarly, we build out views around client and server network delay, but ultimately having some insight into what applications right at this moment are experiencing delay can be very powerful. So again, with dashboard views, it's all about building data sources and then applying them to real-time data streams. So something, you can describe some behavior in the reporting engine and then ultimately turn it into a gadget that's now going to say, I'll constantly review the last X minutes, last 5, 15 hour, whatever it may be, last day, summarize what we've seen, and then just give it at a nice high level view. An additional benefit to using these views is at any point in time, we can actually click into any of them and get the full report view that supports the data that we're actually looking at in the front end. So we have this here, which is our application delay. We can see there's 3 columns. We have our client delay, server delay, and application delay. We talked about how those are derived. Whenever you're in any view in the product, whatever column you're actually sorted on will be the column of focus, the one that's going to be charted in the graph. And then ultimately, if you turn that into a dashboard gadget like we pivoted from, it'll be the focus of that view. But again, this gives us a quick place where we can take that site, see all of the applications that are running there, and then immediately get some insight into which one, is performing the worst from a client network side perspective, a server network perspective, and then ultimately an application delay perspective. If there's some VoIP conversation, that's what's been reported as user impact. We can go across and immediately kind of enumerate if that issue lays on the network side or the application side. If it's the application side, then obviously we can kick that over to the app team, talk about what is being observed, and provide, again, some hard evidence that shows that that's the case. Really, hopefully, kind of rebuffing any attempt to blame the network, because we've now kind of demonstrated it's not the case. Or in the unfortunate situation where you do end up seeing a much higher metric on client or server delay, that's where you can start to get into DSCP and actually check how packets are marked. So in a default view, let's see, I think we've got, it might still be labeled as type of service being the older kind of name for the field on packets that's now used for DSCP and ECN. But if we go in, take a look at some kind of short time frame, maybe the last 15 minutes, we can actually go in, see how packets were marked, and see if our intent for classification has been preserved as we're moving across the network. So again, we see in that high level overview of a retail network, there's lots of hops in it, your local store, the actual application settings for how they'd like to mark their DSCP values. And then again, many places in the network that might have reshaped that traffic. By collecting the information from a latency and jitter perspective on IPFIX and NetFlow data, it also allows us to kind of pivot laterally over into the same records and the DSCP values that were observed on them. So immediately we can see, when server network delay was high, can enumerate all the interfaces that are going to be on the server side of that conversation, take a look at how the traffic actually has its DSCP value set. If it's just assured forwarding to like a higher priority class, we start to get an idea why maybe things are being held up, waiting in queues to move along, all the way down to, we don't have a lot of network delay. Everything's already in express forwarding, and we can show that this is an application problem. So again, it's lots of data, lots of metrics to kind of reframe the issue, and then ultimately provide hard evidence that we can show where performance degradation should be attributed to against the two sides of things. So perfect. So that's really the two main components of breaking down delay from the TCP perspective, and then ultimately instability from the RTP perspective. And again, keeping those metrics for long periods of time in IPFIX and NetFlow data, again, allowing us to go back to when the issue was actually observed and not relying on having to recreate a situation or make assumptions about the network state or the application state at the time that a performance issue was observed. So again, keeping all of these metrics makes it very easy to transact with other functions in the organization, prove to them where the issue lies, and then ultimately move forward. And then again, as we saw for actual networking problems, we can now go in hop by hop, take a look at how traffic's been classified, what its DSCP markings look like, and see if there's any way to maybe categorize our classification at various hops to prioritize that application and move it up through the queue. But otherwise, that is really kind of the main focus of how we can apply these metrics into our network. And I hope you guys will join us for the next talk we're going to do, cut through the complexity, full network visibility, and faster root cause analysis. We're going to start to take a look at how we can use the LLM chat agent that we've integrated into the next release of the product to really jump around through network observability data in a kind of new and fun way that helps us get right to the issue of a problem rather than kind of wrestling with the tools that help us get there. Thank you.
Great stuff, Adam. Yeah, and I'll echo, join us next time around, September 16. And in the meantime, I know we put it in the description. We'll include it with the follow-up. But in the meantime, you can also get the Plixer field guide. So we're essentially going through all the use cases in the field guide, presenting them in these various sessions, getting a bit technical with the data scientist at Plixer. So really fascinating stuff. And my prediction came true. So luckily, within 30 seconds after handing it over is when the worker. So you might even hear the chow chow barking in the background. But with that, come visit us on the socials. We got Plixer on LinkedIn, at Plixer on the Twitters, at Plixer1 on the YouTubes. Like, sub, and share. And for my good buddy, Adam, I'm Peter, and we're with Plixer. Thanks for watching. Say bye, Adam.
Bye, everybody.